From 2009 onward, the Kepler Space Telescope held a fixed gaze on a single region of sky, a wide, dense patch along the plane of the Milky Way, where the constellations Cygnus and Lyra meet in the northern sky, thick with stars pressed close together in the long view from Earth. The telescope did not move its gaze. It did not sweep or scan. It simply watched without interruption, registering the brightness of each star in its field of view across 4 unbroken years, accumulating measurements with the patience of an instrument that had no other purpose and no reason to look away. There were more than 150,000 stars in that field. Each one had been assigned a catalog number before the mission began, a unique entry in the Kepler Input Catalog, a long list of stellar objects identified in advance so that the telescope's photometric data could be matched to individual stars and tracked across time. Most of those 150,000 numbers would never become famous. Most would contribute their quiet data to statistical studies of stellar populations, or to the growing catalog of confirmed exoplanets, and remain known only to the astronomers who needed them. The 8,462,852nd entry on that list was, for the first few years, no different from the rest. It sat in the constellation Cygnus, the Swan, not a star visible to the naked eye under ordinary conditions, not a landmark in the sky that anyone pointed out to a child on a summer night. It was a faint point of light in a field of faint points of light, part of the dense stellar background that gives the Milky Way its soft, unresolved glow when seen from a dark hillside. For the first several years of Kepler's primary mission, it did its job, which was simply to exist, to shine, and to allow the telescope to record its light. The catalog entry accumulated its photometric data alongside every other star in the field, and nothing about the numbers it produced suggested it would one day be the subject of papers submitted to 3 separate journals, or the object of radio searches by professional SETI researchers, or the star that briefly became, in the fall of 2015, the most discussed object in the observable universe. The star's catalog number, KIC 8462852, would eventually be set aside in favor of a shorter name, one borrowed from the researcher whose careful attention first brought it properly into view. But the number comes first, because the number is where the story begins, in a long bureaucratic list of stellar objects assigned before anyone knew whether any particular entry would turn out to be remarkable, waiting in the catalog for whatever the data would eventually say about it. The Kepler Space Telescope was launched on the 7th of March 2009 from Cape Canaveral on a Delta II rocket and settled into an Earth-trailing heliocentric orbit, following Earth around the Sun rather than orbiting Earth itself, drifting slowly away from our planet across the years of its operation. The orbit was chosen carefully. Stationed in orbit around Earth, the telescope would be periodically blocked from viewing its target field by the planet itself, producing gaps in the data. Trailing Earth in a solar orbit instead, with no such obstruction, Kepler could hold its fixed gaze continuously. The design of the mission reflects a specific kind of scientific patience, an understanding that the most useful thing the telescope could do was simply to watch without interruption for as long as the instrument held. The method it used to watch was transit photometry. When a planet passes in front of its host star, as seen from the telescope's vantage point, it blocks a small fraction of the star's light, producing a measurable dip in the star's observed brightness. The dip is small. A Jupiter-sized planet transiting a sun-like star reduces the observed brightness by roughly 1%, but Kepler was built to detect dips that small and smaller. The method requires patience of its own kind. A planet must transit its host star once per orbit, and if the orbit is long, the transits are infrequent. To confirm a planetary orbit statistically, the mission needed to observe at least 3 transits, which meant for planets in the habitable zones of sun-like stars, watching the same stars for years. The 4-year primary mission was designed around exactly that timescale. What transit photometry produces for each of the 150,000 stars in Kepler's field is a light curve, a graph of the star's brightness plotted across time. For most stars, the light curve is a flat, essentially horizontal line, with any transiting planets appearing as small, regular, symmetric dips, clean V-shapes that repeat at precise intervals corresponding to the planet's orbital period. The shape of the dip carries information. How wide it is tells you how long the planet took to cross the stellar disk. How deep it is tells you what fraction of the star's light was blocked. And the symmetry of the slopes on either side tells you whether you are looking at a solid body in a stable orbit. For most of the 150,000 stars, the light curves behave as expected. The planets are there, or they are not, and the graph is orderly in either case. The light curve for KIC 8462852 was not orderly. The first people to notice this were not professional astronomers working through the data systematically. They were volunteers, members of the public who had signed up to participate in the Planet Hunters project through the Zooniverse platform, an online framework built around the idea that human pattern recognition, applied at scale, could accomplish things that automated pipelines could not. Planet Hunters gave registered volunteers access to Kepler light curves and asked them to identify candidate transit signals that the automated detection algorithms might have missed, particularly unusual or irregular patterns that the algorithms were not specifically designed to flag. By 2011, when the relevant data from KIC 8462852 began appearing in the volunteer review queues, thousands of people around the world had participated in the project, reviewing hundreds of thousands of light curves between them, developing an intuitive sense of what a normal light curve looked like and what an anomalous one did. The volunteers who encountered KIC 8462852's light curve paused. The graph on their screens showed something that did not look like any planetary transit they had seen. It did not look like a single clean dip. It did not look like the expected V-shape. The brightness fluctuations they were looking at were irregular, asymmetric, and to their eyes, trained by hundreds of thousands of comparison cases, simply unlike anything the Kepler data had produced before. On the internal discussion boards of the Planet Hunters project, multiple volunteers filed notes on the light curve, and the language they reached for, working without technical vocabulary, was the language of someone who could see that something was wrong without yet being able to say precisely what. The word that appeared in those discussion threads, typed by volunteers sitting at kitchen tables and in spare bedrooms on ordinary evenings in 2011, was the word that would follow this star for years. They called it bizarre. The informal designation that circulated among Planet Hunters volunteers for the class of light curves they found most unusual was WTF stars. The initials stood, in the academic language that would eventually make it into print, for where's the flux? Flux being the technical term for the measured brightness of a star at a given moment, and the question being the one the data most obviously posed. The label was irreverent in the way that collaborative, informal scientific work sometimes is. It was also precise. The flux was demonstrably somewhere other than where it should have been. The Zooniverse platform was designed to route notable findings toward professional researchers who could evaluate them further. The flagged cases from the KIC 846-2852 discussion threads made their way through this process to the attention of a postdoctoral researcher at Yale University named Tabetha Boyajian. Boyajian was working in stellar astrophysics with research interests in stellar populations, binary stars, and the photometric behavior of individual stellar objects. The forwarded thread from the Planet Hunters boards arrived in her correspondence in 2013, along with the light curve for KIC 8462852. She opened the file and saw what the volunteers had seen. The light curve rendered on her screen did not look like the data from a planetary transit. It did not look like an instrument error, or like the regular variation produced by a pulsating star, or like the predictable oscillation of a binary system. It looked like something else, something that the existing library of Kepler light curves did not contain a close match for. The dips in the brightness record were deep, far deeper than any planetary transit could produce. They were asymmetric. The drop in brightness happened at a different rate than the recovery, which is not what a solid spherical body in a circular orbit would produce. They were irregular. They did not repeat at any predictable interval. The light curve had the overall shape of something that was not following any rule that the data allowed her to immediately identify. Boyajian began working through the data in earnest. The process of investigating an anomalous light curve in the Kepler dataset is not quick. The photometric record needs to be examined for instrumental artifacts, systematic errors introduced by the telescope itself, by pixel saturation, by pointing drift, or by any number of other technical effects that can introduce false signals into the data. The surrounding stars in the field need to be checked to ensure that the signal is not being contaminated by light from a nearby object. The background level needs to be assessed. All of this work is methodical and slow, and it is the part of the investigation that the public account of any discovery rarely describes in detail. It is also the part that matters most. A researcher who skips it may spend years studying a feature of the data that is not real. Boyajian did not skip it. What the methodical review of the KIC 8462852 data confirmed was that the anomalous features of the light curve were not instrumental artifacts. The dips were real, the asymmetry was real, the depth was real, the irregularity was real, something associated with the star itself. Whether the star or something in its vicinity was producing these fluctuations, and the fluctuations did not match the expected signatures of any of the standard categories of stellar photometric behavior that the Kepler mission had been designed to detect and classify. The star was behaving in a way that the available explanatory framework did not easily account for. KIC 8462852 sits in the constellation Cygnus, the Swan, a prominent summer constellation in the northern hemisphere, identifiable by the bright star Deneb at the tail of the Swan and the long cross shape of the Northern Cross asterism that runs through it. The star lies approximately 1,470 light-years from Earth. That distance is significant to hold in mind. Light, traveling at approximately 299,792 kilometers per second, takes 1,470 years to cross that distance. The light that Kepler detected from KIC 8462852 during its primary mission left the star sometime around the 6th century of the Common Era, when the Western Roman Empire had already ended, when the Hagia Sophia in Constantinople was newly completed, when the Silk Road trade routes were in active operation. That light was already old when it arrived at the telescope's photometers. It had been traveling since before most of the buildings currently standing in Europe had been conceived. The star itself is classified as an F3V main sequence star, a stellar type that is somewhat hotter, more luminous, and physically larger than our own Sun. Where the Sun has a surface temperature of approximately 5,778 Kelvin, KIC 8462852, burns at approximately 750 Kelvin, a temperature that pushes its emitted light toward the blue-white end of the visible spectrum, giving it a slightly different color than the yellow-white of our own star, as seen from space. F-type main sequence stars are well understood. They are not a category known for dramatic, irregular photometric variability. They do not pulsate in ways that would produce large asymmetric dips in their light curves. They are, in the vocabulary of stellar classification, ordinary. This is one of the things that made the data from KIC 8462852 strange. From the beginning, the star had no obvious intrinsic reason to behave the way it did. Boyajian coordinated the formal investigation of the data across an unusually large team. The paper that eventually emerged from the work carried approximately 40 co-authors, a number that included professional astronomers from multiple institutions, alongside named citizen science contributors from the Planet Hunters volunteer community. The decision to include the volunteers as credited authors was deliberate and meaningful. It acknowledged that the initial recognition of the anomaly had come from their careful attention, and it reflected a model of scientific work in which the boundary between professional and amateur contributions is permeable in ways that occasionally produce important results. The Planet Hunters volunteers had looked at a graph and typed the word bizarre into a discussion thread. That act of attention was now, a few years later, part of the formal scientific record. The paper was submitted to the monthly notices of the Royal Astronomical Society, one of the oldest and most established journals in the field of astronomy, published by the Royal Astronomical Society in London. The peer review process, in which submitted manuscripts are evaluated by independent expert reviewers before acceptance for publication, is the mechanism by which scientific claims are formally vetted before they enter the permanent literature. The Boyajian paper passed through that process and was accepted for publication. It appeared in the journal's September 2015 issue under a title that preserved the informal spirit of the volunteer designation that had started the investigation. The title was, "Where's the Flux? Stellar Flux Dips of KIC 8462852. Mine." The paper's full title, printed at the top of the first column of the first page, carried within it, for anyone who had followed the story from the beginning, a kind of archaeological record. The informal label that volunteers had coined in discussion threads, the playful abbreviation, the direct question, had made it into the headline of a peer-reviewed paper in one of the most respected journals in astronomy. The volunteers were in the author list. The star they had flagged as interesting was now in the permanent scientific literature, and the question in the title was genuinely, formally, unanswered. The paper's structure followed the conventions of astrophysical literature, an introduction establishing the context and the observational record, a methods section describing how the data was analyzed, a results section presenting the photometric measurements and their characteristics, and a discussion section working through the possible explanations for what the data showed. It is the discussion section that has been returned to most often in the years since. The paper examined multiple natural mechanisms for the observed brightness fluctuations, various categories of stellar behavior, various classes of orbiting material, various geometric configurations of occluding objects, and worked through each with care, noting which features of the data each proposed explanation could and could not account for. The conclusion the paper arrived at was not a confirmation of any single explanation. It was something less tidy, and for that reason, more honest. None of the proposed natural explanations, the paper's authors concluded, fully accounted for all of the observed features of the light curve simultaneously. The depths were too large for some proposals. The asymmetry was incompatible with others. The lack of predictable periodicity ruled out a third category. No single model passed every test. The paper's central question, the one that had been the title since the volunteers first coined the label, was left formally open. In published scientific literature, this is a relatively rare posture for a paper to take. Most papers present a finding, a conclusion, a result, something that advances the state of knowledge in a specific direction. A paper that formally concludes that the phenomenon it has investigated is not yet explained is a more unusual document. It enters the literature not as an answer, but as a precisely described question. The 2015 Boyajian paper was that kind of document, and its formal openness, the fact that the authors had done the work carefully and still could not close the question, was itself a signal to the field that something genuinely interesting had arrived. The star itself continued to shine through all of this, unconcerned. It had been shining for approximately 2 billion years, estimated from its stellar classification and its position on the main sequence. It was not at the beginning of its life, nor near the end. It was an ordinary F-type star at midlife, burning steadily in the dense stellar background of the Cygnus arm, its light crossing 1,470 years of space, to arrive at a telescope and produce a graph that a volunteer at a kitchen table in 2011 looked at and could not find words for beyond. This one is different. The Kepler Space Telescope, for its part, held its gaze. The telescope had been designed for patience, and patience was what it delivered. Across the 4 years of its primary mission, it registered the brightness of KIC 8, 462852 at regular intervals, accumulating a photometric record across thousands of individual measurements. The photometers did not know they were watching something unusual. The instrument did not flag the data as anomalous. The telescope simply recorded what arrived at its sensors, converted it to numbers, and transmitted those numbers to the ground, where they waited in a database for a researcher with a forwarded discussion thread to open the file and look at them carefully for the first time. There is something particular about the physical circumstance that produced the discovery of KIC 8, 462852's strangeness, the specific chain of people and processes that led from a telescope in a heliocentric orbit to a discussion thread, to a researcher at Yale, to a journal paper with 40 co-authors. The telescope was built by engineers. The catalog was assembled by scientists. The data was processed by algorithms and made publicly available through a platform that invited ordinary people with no professional credentials to look at it and report what they saw. One of those ordinary people sat down at a screen on an evening in 2011 that was probably otherwise unremarkable and looked at a graph and recognized that the graph was doing something it should not do and wrote a word into a text box. The word traveled through the platform's architecture to a database of flagged observations, and from there to a forwarded email, and from there to a screen at Yale University, and from there to a paper in a major journal, and from there to the permanent scientific literature. That chain of attention, each link of it necessary, none of them sufficient alone, is worth resting on for a moment. The catalog number, the telescope's patience, the volunteer's recognition, the researcher's methodical care, the journal's process of review. The discovery of something unusual in the universe is often imagined as a single dramatic moment, an astronomer at a telescope, a screen suddenly lighting up, an obvious signal. The discovery of KIC 8462852's strangeness was not like that. It accumulated across years and across many people. It became visible slowly through layers of careful attention in the way that most things in science become visible. The September 2015 paper arrived in the literature as the formal beginning of a record that had already been building for years. It established the observational facts as they were then understood: the depths of the brightness dips, their asymmetric profiles, their irregular recurrence, the categories of natural explanation that had been considered and found insufficient. It placed KIC 8462852 in the permanent scientific record, not as a solved problem, but as a documented anomaly, a star whose behavior had been carefully observed and carefully described, and for which the available explanations, as of that date, were inadequate. The final sentences of the paper's conclusion held the question open in the precise, restrained language of formal scientific writing. No known explanation, the authors wrote, fully accounted for all of the observed features of the data. The investigation had produced a detailed, reliable description of the phenomenon. The phenomenon remained unexplained. That open-ended sentence, plain, understated, formally stated, sat on the printed page of the September 2015 issue of the monthly notices of the Royal Astronomical Society, and it has not been fully answered since. The star is still there, in Cygnus, 1,470 light-years away. The data is still in the archive. The question that the volunteers first put into words in a discussion thread in 2011 and that the paper formally codified in 2015 is the same question that the data has continued to pose in the years since: patient, persistent, unhurried, waiting in the light curve for whoever looks at it next, with the attention it requires. The Kepler Space Telescope went on watching for as long as it was able. The star went on dimming on its own irregular schedule. The paper sat in the literature, its conclusions stated plainly and left open as an honest account of something the data describes and the current understanding of the natural world does not fully explain. There was nothing alarming in any of this. There was simply something odd, the specific, quiet oddness of a thing that does not fit the pattern, noticed first by someone at a screen on an ordinary evening, and still, after years of careful attention, not entirely accounted for. The constellation Cygnus, when it crosses the summer sky in the northern hemisphere, carries within it more stars than a casual observer would think to count. They merge into the background glow of the Milky Way's plane, a wash of faint light where the stellar density is highest, where the view from Earth looks deepest into the disk of the galaxy. KIC 8462852 is in there somewhere, too faint to see without a telescope, identifiable only by its coordinates, indistinguishable from the surrounding field except in the photometric record that describes how its brightness has changed over time. The strangeness of the star is not visible. It is only legible, and only to someone who has looked at the right data with the right kind of attention. That is how the discovery happened, not through a dramatic observation, not through a dedicated search for anomaly, but through the quiet accumulation of numbers and the careful attention of people who looked at those numbers and noticed something. The telescope held its gaze. The data accumulated. A volunteer typed a word. A researcher opened a file. A paper was published. The question was stated, formally and plainly, and left open in the literature. The specific, clean kind of openness that marks a genuine scientific problem rather than a defeated one. The star's light had been traveling for 1,470 years when Kepler first measured it. It was traveling still when the paper appeared in print. It is traveling now, crossing the same distance it has always crossed, arriving at whatever instruments are pointed at it, still producing a photometric record that does not entirely conform to what the available explanations would predict. The question that the September 2015 paper left open is still the question, and the data that the paper described is still the data, and the star that produced it is still there, in Cygnus, behaving in a way that no one has fully explained, an entry in a long catalog, a graph on a screen, a question formally stated and formally left unanswered, sitting quietly in the archive for anyone who wants to look at it. The Kepler light curve for KIC 8, 462852, is a graph that looks for most of its length like a nearly flat line. The baseline is steady. The brightness reading holds close to one consistent value, hour after hour, day after day, across most of the 4-year observational record. And then there are the dips. The deepest of them drops the star's observed brightness by approximately 22%. That number carries more weight when it is set beside a comparison. A Jupiter-sized planet, the largest category of planet known to transit a star in a way detectable by the Kepler instrument, produces a brightness reduction of roughly 1% when it passes across the face of a sun-like star. 1%. The dip recorded in the KIC 8 462852 light curve is more than 20 times deeper than that. A planet capable of producing a transit dip of 22% would need to be roughly 5 times the diameter of Jupiter, a body so large it would not, by current models of planetary formation, be a planet at all. That single number, 22%, is the first thing that tells the observer that whatever is moving in front of this star is not a planet. The shape of that dip carries its own information. A planetary transit, when drawn as a light curve, produces a characteristic profile, a relatively smooth, symmetric descent as the planet begins to cross the stellar disk, a flat floor, while the planet's silhouette is fully against the face of the star, and a recovery that mirrors the descent almost exactly. The shape is clean, it is symmetric. Its proportions can be used to calculate the size of the planet and the inclination of its orbit with a good degree of precision. What the light curve of KIC 8 462852 shows, instead, is something that resists this kind of clean geometric reading. The descent into the dip does not mirror the ascent out of it. One side slopes steeply and quickly. The other recovers at a different rate, across a different span of time, tracing a different shape on the graph. The dip is asymmetric. It is lopsided. The two halves of the event do not reflect each other, and that asymmetry, quiet as it is in the graph, carries a significant implication. Whatever is crossing in front of this star does not have the simple, coherent geometry of a sphere moving in a stable path. Astronomers who work with transit photometry have a specific vocabulary for this asymmetry. The descent into a transit event is called the ingress. The recovery is called the egress. When ingress and egress differ from each other in slope, in duration, in shape, the difference encodes information about the structure of the occulting body, whether it has a trailing component, whether it is irregular in outline, whether it consists of more than one object. In every major dip recorded in the KIC 8 462852, Kepler data, ingress and egress differ. In some events, the ingress is steep and the egress is drawn out and gradual. In others, the relationship is more complicated still. The asymmetry is not a consistent pattern that repeats in the same way each time. Each event has its own profile. Each one is differently lopsided. That lack of consistency between events is itself a data point. It suggests that whatever is producing these dips is not a single stable structure, but something that changes, or something that presents a different face to the observer each time it crosses the line of sight. Boyajian's 2015 paper named individual dip events by their timing in Kepler barycentric Julian day notation. These names, precise, numerical, dry, became the working labels that researchers used in subsequent analyses. Dip 800 is among the most discussed. Its light curve, when examined closely, does not show a single descent and recovery. It shows multiple, closely spaced subdips, a series of smaller, irregular notches that descend and return across roughly a week of observational time, giving the event a jagged, saw-toothed profile rather than the single smooth plunge of a coherent body. The subdips are not evenly spaced. They are not the same depth. They do not repeat with any internal regularity. What dip 800 looks like in the graph is the light curve of something that is not one thing, something made of multiple components, possibly loosely associated with one another, passing across the star in a loose, disordered progression rather than a single coherent silhouette. The event designated dip 1500 is the longest and in many respects the most structurally complex of the major dip events in the Kepler record. It is prolonged. Its total duration, measured from the point where the star's brightness begins to drop from its baseline to the point where it returns to that baseline, extends across several weeks of observational time. Within that extended event, the light curve shows internal features that resist simple geometric modeling. There is a plateau mid-descent, a point where the brightness stops falling for a period before resuming its decline. There is a brief partial recovery within the event itself, a small upward movement of the brightness reading before it drops again. The ingress and egress slopes are unequal, as with other dip events, but the dip 1500 profile is also internally uneven in ways that the other dip events are not. To produce a transit light curve with that many internal features, a plateau, a partial recovery, unequal slopes, an extended total duration, the occulting material would need to have a correspondingly complex spatial structure, extended, irregular, perhaps distributed in multiple distinct components strung out along its direction of travel. No single orbiting body, and no pair or small group of orbiting bodies in any straightforward configuration produces a transit light curve with the features visible in dip 1500. The event's complexity is not incidental to the puzzle of KIC 846-2852. It is one of the reasons the puzzle does not resolve cleanly. Any model that accounts for the depth and shape of one dip event must also account for the depth and shape of every other dip event in the record. A model that explains dip 800's multiple subdips must also explain dip 1500's plateau and partial recovery. A model that explains the asymmetric profile common to most of the major events must also explain why the asymmetry differs between events rather than remaining consistent. The light curve as a whole sets constraints that any proposed explanation has to clear, and the constraints set by one part of the data add to the constraints set by every other part. The dip events themselves vary widely in duration. Some of the shorter dip events in the record last only a few days from initial ingress to final recovery. Others extend across several weeks. There is no consistent, statistically repeating duration pattern that would be expected from even a chaotic collection of material maintained in any stable orbital geometry. If a swarm of objects were orbiting KIC 8, 462852 in a stable configuration, crossing the stellar disk repeatedly, their transit durations would be related to their orbital period and their physical extent, constrained by the geometry of the orbit and the star. The range of durations actually observed is wide enough that it does not suggest a single coherent swarm in a single stable orbit. The variation implies either a wide spread of orbital periods or a structure that changes substantially between transit events, or material distributed across a considerable range of orbital distances from the star. The recurrence timing of the dip events adds a further layer of complexity. The intervals between major dip events in the Kepler data are not periodic. They do not repeat at any consistent cycle length. Some pairs of major dip events are separated by hundreds of days. Others occur in relatively rapid succession. Periodic behavior, a consistent repeating interval between successive transits of the same body, is what the Kepler mission was designed to detect. It is the signature that identifies an orbiting planet. The absence of any detectable periodicity in the KIC 8 462852 dip events is one of the fundamental reasons a straightforward planetary explanation was ruled out from the initial analysis. An orbiting body, or a collection of bodies maintaining any fixed orbital arrangement, produces dips that return on a schedule. These dips do not return on any discernible schedule. It is worth sitting with what these two features mean together: the variable shapes of individual dip events and the non-periodic intervals between them. Taken separately, either one could in principle be explained by a sufficiently complex arrangement of matter in orbit. A very irregular body might produce an asymmetric transit profile. A collection of many bodies at slightly different orbital periods might produce a recurrence pattern so complex that it appears irregular at first glance. But together, across an observational baseline of 4 years and dozens of documented dip events, the combination of shape variability and non-periodicity points towards something that is not a clean orbital system of discrete, stable bodies. The data describes something more loosely organized, something that does not hold a fixed structure, something that changes between events, or that produces a different cross-section each time it passes in front of the star. In 2016, Benjamin Montet and Joshua Simon published a dedicated analysis of the KIC 8 462852 Kepler data that addressed a dimension of the star's behavior distinct from the individual dip events. Their analysis worked at the level of Kepler's pixel-by-pixel photometric data, the raw lowest-level data from the spacecraft's detectors, and tracked the star's overall brightness, not event by event, but across the full span of the 4-year primary mission baseline. What they found was a slow, steady, gradual fading of the star's total flux across the entire observational period. This is not the same as the sharp, discrete dipping events. It is a separate phenomenon, a quiet, sustained decline in the star's overall brightness, unfolding across 4 years rather than across days or weeks. The total magnitude of this long-term fading across the Kepler primary mission amounted to approximately 0.5% to 1% of the star's total flux. That may seem small beside a 22% dipping event, but a sustained brightness decline of that magnitude across 4 full years of photometric data is not easily explained by random measurement noise or by the statistical scattering of individual data points. Montet and Simon were careful and systematic in ruling out instrumental causes. They examined the Kepler spacecraft's detector calibration data. They checked whether the trend appeared consistently across all pixels attributing flux to the target star, or whether it was confined to a region suggesting instrumental drift. They worked through the reduction pipeline and the photometric calibration procedures in detail. The fading, they concluded, was real. It was present in the stellar signal. It was not an artifact of the instrument. The methods Montet and Simon applied to confirm this are worth staying with for a moment. The Kepler spacecraft accumulated photometric data over 4 years of uninterrupted operation in its primary mission configuration. Over that period, the spacecraft's detectors aged incrementally, and the observational pipeline included corrections designed to account for these gradual instrumental changes. Any claim of a real long-term trend in a star's brightness requires demonstrating that the trend is present in the stellar signal after all applicable instrumental corrections have been applied, that it is not simply a residual artifact of the spacecraft's own gradual aging. For KIC 8462852, Monte and Simon compared the star's behavior against control samples of similar stars observed by the same instrument under the same conditions. The long-term fading was not present at the same level in the comparison sample. It was specific to KIC 8462852. That specificity is what placed the result on firm footing. The slow secular fading and the sharp discrete dipping events are two distinct observational phenomena occurring in the same star. They operate on different timescales. They have different amplitudes. They present different morphologies. The dipping events are sharp, transient, irregular interruptions of the light curve. The secular fading is a persistent, quiet, sustained trend underlying everything else. Whatever mechanism produces the dipping events may or may not be related to whatever mechanism produces the long-term fading. The two behaviors could share a common cause. They could be independent phenomena occurring in the same system simultaneously. What they cannot both be, without some further explanatory framework, is fully accounted for by the same simple model. The baseline of the light curve, the brightness level from which dips depart and to which they return, was itself, according to Monte and Simon's analysis, slowly declining across the span of the Kepler observations. The dips were occurring against a background that was itself moving, slowly, downward. A researcher examining only the dip events without the long-term trend would have an incomplete picture of the star's behavior. A researcher examining only the long-term trend without the dip events would also have an incomplete picture. The full observational record requires holding both in view simultaneously, which adds a layer of complexity to the already complicated problem of accounting for the dip event morphology. Any proposed explanation for what is happening at KIC 8462852 carries the burden of explaining not just the depth and shape of the individual dipping events, but also the quiet separate fact of the star gradually losing brightness over years. There is a helpful way to hold the scale of the 22% dip in mind without working through the arithmetic each time. A simple visual comparison carries it cleanly. Imagine two graphs placed side by side, each showing a transit event in the same scale and time window. The first graph shows a typical transiting planet, a clean, symmetric, shallow dip that falls perhaps 1% below the baseline and recovers at the same rate it descended. The shape is almost elegant in its regularity, a smooth U with gently sloping sides. The second graph shows one of KIC 8462852's major dip events. The descent is not a gentle slope. It falls more than 20 times deeper than the first graph's dip. The floor, where it exists, is not flat or predictable. The recovery on the far side does not mirror the descent. The second graph's dip is a ragged asymmetric plunge that covers a scale the first graph barely reaches, settling in a region so far below the baseline that the first graph's dip appears, by comparison, like a mild fluctuation rather than a distinct transit event. The visual scale of the difference is one of the things that made the citizen scientists working through Planet Hunters flag this star as immediately, distinctly unusual. It was not a matter of subtle statistical significance. It was visible, clearly and directly, as something of a different kind. The individual dip events span a range of depths as well as durations. Not every dip recorded in the Kepler data reaches the 22% maximum. Some of the events are shallower, a few percent deep, or a fraction of a percent. The record contains a distribution of depths as well as a distribution of shapes and durations. That distribution itself carries information. If the occulting material came in consistent, well-defined parcels, discrete objects of roughly similar size, arriving in front of the star at roughly similar orbital distances, the distribution of dip depths would be relatively constrained. The actual distribution, spanning from very shallow dips to the 22% maximum, is broad. The occulting material, whatever it is, presents a wide range of effective cross-sections to the observer. Its depth profile varies as much as its shape profile and its timing profile. Monte and Simon's 2016 paper noted something further about the structure of the secular dimming trend within the 4-year baseline. The fading was not perfectly linear across the full observational period. There were sub-intervals within the 4 years in which the fading rate appeared to be faster, and sub-intervals in which it appeared to slow. This internal structure within the long-term trend, variation in the rate of the secular fading itself, adds another layer of complication to the already complex observational picture. A steady linear fading across 4 years would be more straightforwardly modeled as a gradually increasing obscuration by some persistent material. A fading that itself varies in rate requires a more dynamic underlying process, one that changes in intensity or configuration over the timescales of months to years, not just over the short timescales of individual dip events. The Kepler photometric data for KIC 8462852 was taken over 4 years of nearly continuous observation. That is a long baseline for a space-based photometric mission. It is, at the same time, a very short baseline relative to the processes that might produce the kind of secular fading Monte and Simon detected. A star like KIC 8462852, an F3V main sequence star, moderately massive, moderately luminous, on a stable place in the stellar evolution sequence, does not, under standard stellar physics, change its total brightness by a measurable fraction of a percent over 4 years. The secular dimming, precisely because it is not predicted by standard stellar evolution models for this class of star, requires an external explanation. Something in or around the system is blocking the star's light in a way that accumulates over years rather than only in episodic transit events. That external something, its nature, its geometry, its relation to the bodies producing the individual dip events, is one of the layers of the question that the observational data raises and does not answer. What the Kepler light curve of KIC 8462852 contains, taken as a whole, is a layered set of anomalies. There are the individual dip events, sharp, variable in depth and shape and duration, asymmetric in profile, non-periodic in their timing, with morphological complexity that resist simple geometric modeling. There is the secular trend, a slow, real, gradual fading of the star's total flux across the 4-year baseline, confirmed at the pixel level, not present in comparable stars, observed under the same conditions. These two phenomena share a host star and a photometric record, but they do not obviously share an explanation. They do not obviously require the same mechanism, and together, the constraint they place on any proposed model of what is happening at KIC 8462852 is considerably tighter than either one alone would impose. It is this tightness of constraint The requirement that any satisfying explanation account for both the dip morphology and the secular trend, for both the non-periodic timing and the wavelength behavior of the events, for both the asymmetric profiles and the absence of the infrared excess that a substantial warm debris field should produce, that makes the question of KIC 8462852 genuinely difficult rather than merely complex. Difficult in the specific sense that the observational record does not leave a great deal of room for the simplest natural explanations to operate. Not impossible, not permanently resistant to explanation, but not yet resolved by any model that accounts for all of the documented features simultaneously. Dip 800 sits in the middle of the Kepler baseline. Its multiple subdips, examined carefully, show a characteristic that some researchers noted as suggestive of a trailing structure, a primary component followed by secondary features separated by irregular intervals, each producing its own smaller notch in the light curve. The spacing between subdips within dip 800 is not constant. The depths of the subdips differ. If the subdips represent distinct physical components of a loosely associated structure passing across the stellar disk, those components are not evenly distributed in space and do not present equal cross-sections to the line of sight. They are, in the geometric picture implied by the data, irregular, variably spaced, and variably sized. Whatever produced dip 800 was not a smooth, coherent object. It was something with internal structure that was reflected in the internal structure of the light curve. Dip 1500's profile, by comparison, suggests something that extends over a longer path length across the stellar disk, something with a large spatial extent in the direction of its motion relative to the line of sight, moving slowly enough or extended enough to produce a transit event lasting weeks rather than days. The plateau within dip 1500, the period mid-descent, where the brightness stabilizes briefly, is one of its most discussed features. A plateau in a transit light curve implies that the cross-sectional area of the occulting material has reached a temporary local maximum during the event, that the material, in the projection seen from Earth, has a shape that is wider in some parts and narrower in others, and that the projection happened to be crossing a wider part when the plateau appeared. The brief partial recovery within the event, before a further decline, implies the opposite, a narrowing of the effective cross-section mid-transit, briefly allowing more stellar light through before the coverage increases again. These features are not decorative details. They are direct records of the physical structure of whatever crossed in front of the star during that event. It is also worth noting, in the context of this section's material, what the light curve of KIC 8462852 does not show. It does not show a regular periodic signal of the kind that a large planet in a close orbit would produce. It does not show the clean symmetric transit profiles that would identify a single solid body of fixed geometry. It does not show the infrared brightening that would accompany a large warm debris field, absorbing and re-emitting stellar radiation. All of these absences are data. They constrain the model space in the same way the positive features do. The question of what produces the observed light curve cannot be answered without also accounting for all the things the light curve does not contain, the signals and features that various proposed mechanisms would produce and that simply are not present in the data. The light from KIC 8462852 takes approximately 1,470 years to reach Earth. The dip events recorded by Kepler, dip 800 and dip 1500, and all the others, the secular fading, tracked across 4 years, represent light that left the star somewhere between the 6th and 7th century of the Common Era by Earth's calendar. Whatever was producing those dips was doing so at that time, in that system, 1,470 light-years away. The Kepler spacecraft recorded the arrival of that light as a series of numbers, and those numbers drew the light curve, and the light curve describes something that happened at a remove of 14 centuries and a distance of nearly 9,000 trillion miles. The specific precise strangeness of the KSE 8462852 light curve is the record of something that old and that distant, arriving at Earth's vicinity and being read as a graph. The graph sits quietly on the desk, or on the screen, or printed on a page in the monthly notices of the Royal Astronomical Society. Its flat baseline stretches across most of its horizontal span. The dips appear as they do, irregular, asymmetric, variably deep, non-periodic, some multi-component, some prolonged, none matching the expected profile of a planetary transit or any other class of known transiting body. Below all of it, the secular trend runs slowly downward across the full width of the baseline, the star fading, quietly and gradually, across 4 years of recorded observation, independent of the discrete events would very slake show, a separate persistent signal that Monte and Simon confirmed and published and left, as all the other analyses have left their findings, as part of the open record of a question that the data raises and the data does not yet answer. That open record, the particular shape of the dips, the particular complexity of dip 800 and dip 1500, the measured depth of 22% against the 1% of a planetary transit, the secular fading confirmed at the pixel level, the non-periodicity and the asymmetric profiles and the variable durations, holds 2 layers of unexplained behavior, resting quietly one beneath the other. The sharp events, irregular and complex, that punctuate the 4 years of Kepler observations, and the slow sustained dimming, real and confirmed, that runs through all of it underneath. A second thing that does not yet have an answer, sitting calmly beneath the first. In the spring of 2017, 2 space telescopes and a network of ground-based observatories turned toward the same point in the constellation Cygnus at the same moment. One instrument was sensitive to infrared light, one was calibrated for ultraviolet. A third was watching in ordinary optical wavelengths from a mountaintop in Chile. The star they were all watching had begun to dim again, its brightness falling away in the slow, irregular pattern that had made it one of the most studied single objects in contemporary astronomy. And what those 3 instruments recorded, when their data streams were later compared side by side, was not the same thing. The dimming was real at every wavelength. The depth of it was not. That difference between the ultraviolet reading and the infrared reading, the gap that opened between 2 instruments watching the same event at the same moment, was the clearest physical clue the star had offered to the people studying it. It was not a dramatic clue, it was a quiet one, a number slightly larger in one column than in another. But in that gap, if the physics held, was a signature, and the signature pointed towards something very small. Huan Meng, an astronomer working with data from NASA's Spitzer Space Telescope and the Swift Observatory, led the analysis of that 2017 multi-wavelength campaign. Spitzer recorded in infrared, the long, warm end of the light spectrum, the wavelengths associated with heat. Swift recorded in ultraviolet, the shorter, more energetic end. Both were watching KIC 8462852 during an active dimming event, and both registered a decline in the star's apparent brightness. The Spitzer reading showed a shallower dip. The Swift reading showed a deeper one. The star was dimming more strongly at ultraviolet wavelengths than at infrared ones, and that discrepancy, When Meng and colleagues published their analysis in the Astrophysical Journal, carried a specific physical interpretation. The material blocking the star's light was not large, solid, and opaque. It was small, very small. It was dust. The physics behind this conclusion is a well-established piece of optics, grounded in work developed across the 19th and 20th centuries, and confirmed across a wide range of astrophysical contexts. When light passes through or around a particle, the way it interacts with that particle depends on the particle's size relative to the wavelength of the light itself. A very large object, a boulder, a planet, a solid structure of any kind, large enough to be described as opaque, blocks all wavelengths equally. Red light and blue light and ultraviolet light all cast the same shadow behind a sufficiently large obstacle. Size, beyond a certain threshold, becomes wavelength neutral, but a very small particle, one whose diameter approaches or falls below the wavelength of light it is interacting with, behaves differently. It preferentially scatters shorter wavelengths. It deflects and absorbs ultraviolet and blue light more efficiently than it deflects infrared. The result for an observer watching a star through a cloud of such particles is that the star appears to dim more at short wavelengths than at long ones. The cloud is not uniformly opaque. It is selectively transparent, more transparent to heat and infrared, less transparent to the cooler, shorter, bluer light at the other end of the spectrum. This effect is named for the physicist who characterized it mathematically in the early 20th century. Mie scattering, as it is called, makes specific predictions about the wavelength dependence of extinction by particles of a given size. And when Meng's team applied those predictions to the data from the 2017 monitoring campaign, the numbers aligned with what would be expected from submicron dust grains, particles smaller than 1 micrometer across, roughly the scale of fine smoke, or the smaller particles in volcanic ash, orders of magnitude smaller than a grain of sand. Grains of that size are common in space. They are produced by comets, by collisions between rocky bodies, by the outgassing of volatile material as icy objects are warmed by a nearby star. They are not exotic. They drift through protoplanetary disks, accumulate in stellar debris fields, and trace the invisible architecture of planetary systems still in the process of forming. The dust interpretation of KIC 8462852's dimming events was, in one sense, a tidying answer. It was something familiar placed at the center of something that had appeared deeply unfamiliar. The star that had baffled researchers with its asymmetric, irregular, unprecedented light curve was now producing a signal consistent with well-understood physics. Fine particles scattering short wavelength light, more than long wavelength light, Minchel scattering doing what Minchel scattering does. The instruments had read the signature correctly, and the signature said dust. In another sense, though, the dust answer opened onto a further set of questions that the data had not closed. The first of those questions concerned heat. Any material that absorbs starlight does not simply disappear. It must go somewhere. The energy it absorbs is re-radiated at a longer wavelength, as infrared light, as heat. A warm cloud of dust surrounding or orbiting a star will glow faintly in the infrared, producing what astronomers call excess emission, an elevated reading at infrared wavelengths above what the bare stellar surface alone would produce. This excess is detectable. It has been detected around many young stars as signatures of protoplanetary dust disks, debris belts, cometary activity, and ongoing planetary formation. The instrumentation required to identify it is well established, and the WISE survey, the Wide Field Infrared Survey Explorer, along with the Spitzer Space Telescope, had both been applied to KIC 8462852 specifically because of this question, the answer those instruments returned was consistently negative. KIC 8462852 does not display the elevated infrared emission that a significant warm dust structure should produce. Its infrared readings are consistent with what would be expected from the stellar surface alone, not from a stellar surface partially wrapped in a debris field large enough to account for the degree of optical dimming observed. The star dims by up to 22% in some events. A dust structure capable of blocking 22% of a star's optical light would, by the basic thermodynamics of absorption and re-emission, be producing considerable infrared radiation. That radiation has not been detected at the expected levels. The absence is consistent. It has been checked against multiple instruments and multiple observation epochs. It is not a measurement artifact. The infrared excess that the proposed dust field should produce is simply not there, or at least not there at the magnitude the optical dimming would lead one to expect. This is the central tension in the dust hypothesis, and it is a genuine one. The wavelength-dependent dimming says fine particles, consistent with dust. The absent infrared excess says where is the heat from all that dust. These two observational facts are not strictly incompatible. There are geometric configurations, temperature gradient, there are dust grain compositions that might partially reconcile them, but no single model has been constructed that accounts for both of them cleanly and simultaneously without requiring additional assumptions that introduce their own complications. One possibility is that the dust is very cold, located far from the star, orbiting at a distance where the stellar heating it receives is minimal, and therefore re-radiating at very long infrared wavelengths that are harder to detect and that the available instruments were not optimally calibrated for. Cold dust, distant dust, would produce a fainter and longer wavelength infrared signature, potentially below the detection thresholds of WISE and Spitzer in the relevant survey configurations. This is a plausible mitigation. It does not, on its own, fully resolve the tension and the geometry required to place enough cold dust in the right configuration to block 22% of the stellar flux while remaining warm enough to be present at all, but too cold to be detected in the available bands, is constrained, and those constraints have been worked through carefully by multiple researchers without producing a universally accepted answer. Another possibility involves the geometry of the dust distribution itself. If the material is not a uniform disk or cloud, but instead a highly asymmetric collection of discrete clumps, some of which are optically thick and others of which are largely transparent, then the average dust mass required to produce the observed dimming can be reduced substantially. Less mass means less absorbed energy, means less re-radiated heat, means a smaller infrared excess. Clumpy, heterogeneous dust configurations have been invoked in a number of models of KIC 8462852. They can be made to fit the observed optical behavior reasonably well. They are also harder to constrain from first principles because an irregular, non-uniform dust structure can be adjusted to fit almost any observation without necessarily being physically motivated. The family of comets model, which appeared in the original 2015 paper authored by Tabetha Boyajian and colleagues, approached the problem from a different direction. Comets produce dust. As a comet approaches a star and is heated by it, volatile ices vaporize, releasing gas and carrying small particles off the surface, exactly the submicron scale grains that Meaty scattering theory predicts would produce wavelength-dependent dimming. A cometary body transiting the stellar disk would block some light with its nucleus, but it would block considerably more with its trailing dust tail, and that dust tail would thin and disperse as it extended behind the nucleus, producing the asymmetric light curves observed at KIC 8, 462, 852, a relatively steep ingress as the solid body and dense inner coma precede the star's disk, and a gradual extended egress as the trailing tail of dispersed material slowly clears the line of sight. The asymmetric dip shapes that had seemed so geometrically difficult to explain under simpler models are, in this framework, a natural consequence of how comets move. The cometary model has clear qualitative appeal. It connects a well-known class of solar system object to a set of observed signatures and produces a physically coherent picture in which the behavior, though extreme, is driven by recognizable processes. A comet crossing a stellar disk is not exotic. Comets exist in the outer reaches of most planetary systems, and cometary activity around other stars has been inferred from spectroscopic observations of falling evaporating bodies, the exocomet signals detected in spectra of several stars over the past few decades. Decade 8, 462, 852 is not implausible territory for cometary influence. The difficulty is one of scale. To account for the largest dipping events, a 22% flux reduction sustained across days to weeks, the cometary model requires not one comet or a few comets, but an implausibly large population of them, distributed in a configuration that produces sustained blocking at the observed depths without any plausible dynamical origin that the existing models of planetary system formation readily accommodate. The numbers, worked through carefully, strain the model. A comet produces a dust tail of measurable physical extent, and the amount of dust required to block more than a fifth of the light from an F-type star across a broad angular area is large, very large. Producing that quantity of dust from cometary fragmentation and sublimation requires a reservoir of cometary material that in a mature stellar system like the one KIC 8462852 appears to inhabit would be difficult to explain dynamically. Where did that much material come from, and why is it arriving now, and where does it go afterward? It is possible that a gravitational perturbation, a close encounter with a companion star, or the resonance effects of a massive planet could scatter a large population of outer system bodies inward, producing a pulse of enhanced cometary activity that lasts for a period of years or centuries before the reservoir is depleted. This kind of dynamical upheaval is not without precedent in models of planetary system evolution. The late heavy bombardment period in the early solar system is thought to have been triggered by something broadly similar, a resonance shift in the giant planets that sent a wave of outer solar system objects cascading inward. A scaled-up version of that kind of event applied to another planetary system could in principle generate the cometary activity KIC 8462852 seems to require. The model is coherent. It is also not yet constrained to the specific case. It remains a qualitative possibility rather than a quantitatively verified explanation. All of this, the wavelength dependence, the absent infrared excess, the cometary scale problem, the various geometric and dynamical proposals that partially address each constraint, has been surveyed and evaluated repeatedly in the years since the star first attracted attention. The researcher whose name is most consistently associated with the systematic multi-constraint evaluation of these competing models is Jason Wright of Penn State University. Wright, who works in the area of SETI science and stellar astrophysics, has written both in peer-reviewed papers and in longer technical discussions on his professional blog about the specific challenge of evaluating KIC 8462852, not against one observational fact at a time, but against the full set of constraints simultaneously. The method Wright advocates, and which his writing on the case consistently applies, is to list the distinguishing observational features of KIC 8462852 that any proposed explanation must account for, not some of them, not the convenient ones, but all of them, and then to evaluate each model against each item on that list honestly. The list assembled from the published record contains at minimum 4 major features: the irregular, asymmetric dipping events of variable depth and duration, ranging from small fractions of a percent to 22% flux reduction, the secular, long-term dimming trend across the full Kepler baseline, amounting to approximately 0.5% to 1% of fading over 4 years, the wavelength dependence of the dimming, with deeper dimming at shorter wavelengths consistent with submicron dust, and the absent or low-level infrared excess, inconsistent with the quantity of warm solid material that the optical dimming would ordinarily imply. When Wright works through the proposed explanations against those 4 criteria, the result is consistent and sobering in a quiet way. The cometary model addresses the dip morphology reasonably well and provides a source of the right kind of dust to explain the wavelength dependence, but struggles to account for the secular dimming trend and does not neatly resolve the infrared excess problem. A model involving a disk of occulting material, a warped or inclined debris disk, perhaps the remnant of a large collision, can address the secular dimming and some aspects of the dip behavior, but the wavelength dependence then requires that disk to be composed of fine, warm dust whose infrared signature should be detectable, and largely has not been. Models involving interstellar material are constrained by the star's position and proper motion in ways that make them difficult to sustain across the full duration of the Kepler observations. Intrinsic stellar variability, the possibility that the star itself is the source of some of the flux changes, has been considered and partially ruled out by spectroscopic monitoring that found no corresponding changes in the star's surface activity or chemical composition during the deeper dipping events. Each model, taken in isolation, does something useful. Each model, placed against the full constraint list, leaves at least one item inadequately accounted for. That is not a failure of any individual model, and it is not a failure of the research community that has worked through them. It is a description of where the investigation stands. The evidence is real. The constraints are real. The gap between what any current explanation fully explains and what the data requires is also real. It sits there, not threatening, not dramatic, not the kind of thing that demands a response tonight, but present and honest and genuinely unresolved. There is something worth pausing over in the specific form that this unresolved state takes. Most astronomical mysteries, when they persist, do so because the data are insufficient, too few observations, too much noise, instrumentation not yet capable of resolving the relevant features. The situation with KIC 8462852 is somewhat different. The data are unusually good. Kepler produced 4 years of nearly continuous photometric monitoring at a precision that has rarely been achieved for any other star. The subsequent multi-wavelength follow-up campaigns added infrared, ultraviolet, and optical coverage during active dimming events. The historical record through the Dash Plate Archive and the American Association of Variable Star Observers database extended the timeline of observed behavior backward across more than a century. The problem is not a lack of information. The problem is that the information, gathered carefully and from multiple independent sources does not all point in the same direction. This is a different kind of open question from the ones that simply await better instruments. Better instruments will help, and new monitoring campaigns will add to the record, and future dimming events will be captured with even greater multi-wavelength coverage than what was available in 2017. But the core tension between the wavelength dependence that requires small particles and the absent infrared excess that resists large quantities of absorbing material is not primarily an instrumentation problem. It is a physical modeling problem. The constraints are in the data. What is needed is a physical scenario that satisfies all of them at once. The best current candidate remains some form of dust, cold, fine, asymmetrically distributed, possibly cometary in origin, possibly the product of a recent large collision or a period of enhanced dynamical activity in the outer regions of the star's planetary system. The 2017 Meng campaign, with its clear wavelength-dependent signal, strengthened the case for dust and weakened further the case for any model relying solely on large opaque occluding bodies. That is a genuine advance. It narrowed the field. It pointed the investigation in a more specific direction. What it did not do, and what has not yet been done, is produce a dust model that accounts for the absent infrared excess at the required level without introducing further complications that the data then constrain in other ways. Jason Wright's whiteboard, figurative or literal, in the version of this one might imagine, carries a list that remains at the bottom with items unchecked. Not because the wrong people are working on it, or because the instruments have been pointing in the wrong direction, or because the analysis has been careless. The items are unchecked because the phenomenon is genuinely not yet fully explained. The checklist is a description of what is known and what is not, held honestly, kept current as each new campaign adds to the record. The star continues to dim, the data continue to be collected, the papers continue to be written and reviewed, and cited and extended. Each new campaign constrains the models a little further, eliminates a few more configurations, narrows the range of physically plausible scenarios that can account for everything at once. The process is slow, and the answer, when it comes, will very likely be quiet, a model that works, accepted by a community that has been holding the question carefully for years, the checklist finally complete. For now, the dust evidence is what the data most clearly supports. It is the closest the investigation has come to an answer. It is also examined carefully against all the constraints simultaneously, not quite the whole answer. The star dims more at ultraviolet wavelengths than at infrared ones. The material responsible for that difference is, in all probability, very small and very fine. The heat from that material at the levels required to produce the observed optical dimming is not fully visible in the infrared where it would be expected to appear. That gap between what the wavelength dependence implies and what the infrared absence requires is where the investigation currently rests. Not at the edge of something alarming, not in the territory of something requiring a conclusion other than the ones available from known physics, simply at the honest boundary of what has so far been established and what has not. The dust is real, or something very like dust is real, moving through the line of sight between the star and the instruments watching it. 1,470 light-years away in the direction of Cygnus. What exactly it is, where it came from, how much of it there is, and why the star's infrared does not show what the optical dimming implies should be there. Those questions remain on the list. The list remains open. The star continues its irregular, patient, poorly understood dimming on its own schedule, in its own way, without particular regard for what any model currently proposes. The dimming events have their own names now, informal ones, given by the researchers and citizen scientists who have been watching the star closely enough to feel the weight of each new episode as it arrives. Elsie, Celeste, Skara Brae, Angkor, names given not because the events are understood, but because they are observed with enough continuity and care that they have become, in some sense, familiar. This is what it looks like when a scientific community decides to stay with a question that has not given up its answer. The instruments keep pointing, the data keep arriving, the names accumulate, the checklist sits on the desk, and the dust or whatever moves through the line of sight and scatters short wavelength light more than long wavelength light, more than 20 times the depth of a planetary transit, in shapes and patterns that no current model fully accounts for, continues its quiet work, dimming the star by amounts that vary without pattern, for durations that resist prediction at intervals that carry no regular rhythm, across a timeline that in the historical plate data now stretches back more than a century. The dust hypothesis is careful science, done honestly. It is what the multi-wavelength evidence most directly suggests. It is the strongest current answer to what produces the irregular, asymmetric wavelength-dependent dimming of KIC 8462852. And it is, at the level of the full constraint list, secular dimming, dip morphology, wavelength dependence, absent infrared excess, not yet the complete answer. The item on the right side of the list, the one where the infrared should be and is not, stays unchecked. Quietly and without urgency, it stays unchecked. The instruments that recorded the 2017 Meng campaign, Spitzer watching in infrared, Swift watching in ultraviolet, the ground-based optical network watching in between, gave the investigation its clearest multi-wavelength picture of an active dimming event. The picture said, fine particles. It said, submicron, scattering, consistent with me theory. It said, not large opaque solid bodies. It moved the investigation forward in a specific and useful direction, and it left, at the end of the analysis, a set of numbers that still do not all agree with each other in the way they would need to for the full picture to be closed. That is where the dust argument rests. It is the best current map of the territory. It does not reach the boundary in every direction. The star dims. The dust scatters short wavelength light. The infrared remains quieter than expected. The question, held carefully across years of data and a growing archive of careful analysis, remains open, not in the way of something forgotten or abandoned, but in the way of something still being worked, still being watched, still carrying the quiet patience of an investigation that has not yet arrived where it is going. In September of 2015, a preprint appeared on the Arxiv server, the open access repository where astronomers deposit papers before formal peer review, where the work is available to anyone with a browser and an interest in what other researchers are thinking before the journals have weighed in. The paper's abstract was careful. Its language was qualified. It was 3 pages of measured scientific prose, and near the end of its section on possible explanations, in language that had clearly been drafted and redrafted to sit at exactly the right distance from the claim it was making, it raised a possibility that no peer-reviewed paper had raised before for a real, named, cataloged astronomical object. The authors were Jason Wright of Penn State University, Stein Sigurdsson, and Tabetha Boyajian, the same Boyajian whose name the star would eventually carry informally. The paper did not say that KIC 8462852 was surrounded by alien megastructures. It said only that if one were evaluating a complete accounting of possible explanations for the star's documented dimming behavior, The signatures expected from such a thing would look like this, and would look in several respects like what the Kepler data showed. That is worth sitting with for a moment. The paper did not endorse the hypothesis. It did not place it at the top of its list. It positioned the megastructure possibility as the last resort in a hierarchy of natural explanations, something to be raised because a thorough accounting of the evidence requires considering it, not because the authors believed it was likely. In the language of the abstract and the conclusions section, the framing was explicit. Instrumental artifacts, natural astrophysical phenomena, and conventional explanations should all be ruled out first. What Wright, Sigurdsson, and Boyajian were saying, in the careful grammar of a scientific paper, was that they had looked at the data carefully and could not find a natural explanation that accounted for all of it, and that in a field where the goal is to eliminate possibilities honestly, the megastructure hypothesis belonged in the record. It had been raised. It would need to be tested. That was the extent of what the paper claimed. The intellectual lineage of the hypothesis reaches back to 1960. Freeman Dyson, a theoretical physicist, then at the Institute for Advanced Study in Princeton, published a 4-page paper in the journal Science with the title Search for Artificial Stellar Sources of Infrared Radiation. Dyson was interested in a question that had been gathering weight in theoretical circles since the late 1950s. If other technologically advanced civilizations exist elsewhere in the universe, what observational signatures might they leave that we could detect at stellar distances? His answer was specific and physical. A civilization with access to the full energy output of its host star, he reasoned, would eventually find it advantageous to build a dense collection of orbiting structures, solar energy collectors, habitats, industrial platforms distributed across a wide region around the star, capturing as much of the star's radiated energy as possible. This structure, in its most complete form, would not be a single solid shell, but rather a swarm of discrete objects in close orbits, and it would produce a distinctive observational signature, not the clean symmetric periodic brightness dip of a single planet transiting a stellar disk, but an irregular, non-repeating, asymmetric series of flux reductions, the kind of pattern that a chaotic swarm of objects in various orbital configurations would leave on the star's measured light output. Dyson's paper was short. Its final sentences described what such a thing might look like to a distant observer with a sufficiently sensitive photometer. The paper was published, noted, and filed away as a theoretical exercise. 55 years later, it became directly relevant to a star in the constellation Cygnus. Wright, Sigurdsson, and Boyajian's 2015 paper was the first time in published astronomical literature that a real, specific object in the observational record had been formally evaluated against the Dyson swarm template. That alone was significant, independent of whether the hypothesis turned out to be correct. The scientific community had spent decades discussing what signatures an alien megastructure might produce in principle. Here was a paper saying, we have found an object whose measured characteristics overlap with those predictions. The overlap was not complete. The hypothesis was not confirmed. The paper was not claiming otherwise, but the comparison had been made, formally and in print, and it could not be unmade. Chi C8 462852 was now the first star in the Kepler catalog, or in any catalog, to have been evaluated against a Dyson structure model in a peer-reviewed context. That was a specific documented fact. Whatever happened next, what happened next was, in some respects, entirely predictable. The Arxiv preprint circulated through the astronomical community in September 2015. Word spread through science journalism networks, And on October 13th, 2015, The Atlantic published an article by journalist Ross Anderson with the title "The Most Mysterious Star in Our Galaxy." The article appeared on a Tuesday afternoon. By Wednesday morning, it had been shared hundreds of thousands of times. By the end of the week, by some counts, it had been shared millions of times. Follow-up coverage appeared in virtually every major news outlet and science publication in the world within days. K8462852, which had been known until that week only to the small community of planetary scientists, variable star observers, and citizen science contributors who had followed its development through the Planet Hunters forums and the MROS paper, was suddenly a global cultural phenomenon. The phrase alien megastructure star circulated through social media, through news headlines, through late-night television monologues. Tabby's star, the informal name that would attach to KIC 8462852 in public discourse, derived from Boyajian's first name, became for a period of several weeks one of the most discussed topics in popular science media worldwide. Anderson's article was not reckless. It foregrounded the megastructure hypothesis in dramatic language, as the headline makes plain, but it included the appropriate scientific qualifications and quoted the relevant researchers accurately. The issue was not the article itself, but the way any hypothesis, when framed for a general readership in accessible and vivid language, tends to acquire a solidity in public perception that the underlying science has not yet earned. The word alien in a headline does something to a reader's mind that the phrase low probability hypothesis included for completeness does not, regardless of how carefully the body text qualifies it. What had been a carefully positioned outlier in a scientific paper became, in public circulation, something closer to a frontrunner. The article was read by people who did not have the context to place it within the hierarchy of explanations the researchers had actually proposed. The megastructure hypothesis was interesting. It was legitimately in the scientific record. It was also, in the assessment of the professional astronomical community, the least probable explanation on the list, and that ordering got lost in the speed of distribution. The professional community's response was measured. Papers continued to appear, addressing natural explanations. Researchers reiterated publicly and in print that the wavelength-dependent behavior of K8 8462852's dimming, the fact that it dims more strongly at shorter ultraviolet wavelengths than at longer infrared wavelengths, was itself a significant constraint on the megastructure hypothesis. This is worth understanding in its physical terms because the argument is clear and direct. A large, solid, opaque structure, a satellite, a collector, a shell of engineered material, blocks light in a way that does not depend on the wavelength of that light. A sufficiently large, solid object casts a shadow across all wavelengths equally, because its physical size is many orders of magnitude larger than the wavelength of the light it blocks. Whether the light is ultraviolet at 300 nanometers or infrared at 3000 nanometers, a solid object large enough to block a star will block all of it at the same rate. The dimming will be, in the technical term, gray, wavelength neutral. What KIC 8462852 shows is the opposite of gray dimming. It shows more pronounced dimming at shorter wavelengths and less pronounced dimming at longer wavelengths, which is the signature of fine particles, dust, scattering light in a wavelength-dependent way. Solid megastructures, by their physical nature, cannot produce non-gray dimming. The wavelength dependence of the star's behavior is not a detail that can be set aside. It is a foundational constraint, and it is inconsistent with exclusively large opaque solid bodies as the occulting material. That argument sits on the record clearly, and has done so since the 2017 multi-wavelength campaigns produced their results. The professional consensus, which is not unanimous, but is strong, holds that the most plausible current explanation for KIC 8462852's dimming involves fine dust, submicron particles that scatter short wavelength light disproportionately and would leave a more muted infrared signature than a large solid body. The megastructure hypothesis cannot account for the wavelength dependence without significant modification, and significant modification of the hypothesis to accommodate the wavelength dependence tends to undermine the other aspects of the hypothesis that made it attractive as an explanation for the specific dip morphologies observed. The constraints do not work in the megastructure hypothesis' favor. They did not work in its favor when the wavelength data first appeared, and they have not improved since. The professional community's position that the megastructure hypothesis is the least supported of all proposed explanations reflects that evidentiary situation honestly, not dismissively. Jason Wright himself, whose name is most directly associated with the megastructure hypothesis in the scientific literature, has been clear in his own writing and public communication that the hypothesis sits at the far edge of the probability spectrum. Wright maintains a professional blog called AstroWright, where over the years he has written extensively about KIC 8462852, about the proper scientific treatment of exotic hypotheses, and about what it means to evaluate evidence carefully. His position has consistently been that raising the megastructure hypothesis for formal consideration is not the same as advocating for it, and that the scientific obligation is to test hypotheses against evidence rather than to refuse to name them. What he has argued is that the hypothesis deserves to be evaluated by the data, evaluated and found wanting, if that is what the data show, rather than excluded before the evaluation takes place. That position is methodologically defensible. It is the position one would expect from a scientist who takes seriously both the evidence and the breadth of what should count as a possible explanation. And the evaluation has in fact taken place. The wavelength-dependent dimming has been measured, the constraints have been applied, the megastructure hypothesis has been found inconsistent with those constraints. Wright has not argued otherwise. In the fall of 2015, while the public conversation about megastructures was still accelerating, the SETI Institute directed the Allen Telescope Array toward KIC 8462852. The Allen Telescope Array is a facility located in Northern California, built specifically for the systematic search for radio signals that might originate from technologically advanced civilizations elsewhere in the galaxy. It consists of an array of radio dishes operating together, capable of monitoring a wide range of radio frequencies simultaneously. The Allen Telescope Array had been in operation for several years before 2015, conducting ongoing surveys of target stars and regions of interest. When KIC 8462852 became a public phenomenon, it became an obvious candidate for dedicated SETI observation. If an advanced civilization were engineering structures around that star, there was a reasonable, if not certain, expectation that some form of radio emission might accompany its activities, whether as deliberate communication or as technological byproduct. The Institute pointed its dishes at Cygnus and listened. The observation campaign ran across radio frequencies from 1 GHz to 10 GHz. This range includes what is sometimes called the water hole, the radio frequency band between approximately 14-20 MHz the emission frequency of neutral hydrogen, and 1662 MHz, the emission frequency of the hydroxyl radical. The water hole has been considered by SETI researchers a promising region of the spectrum for interstellar communication, because any civilization familiar with hydrogen and water chemistry, any civilization with a sufficiently developed understanding of the universe to construct orbital megastructures, would likely recognize the significance of these frequencies and might choose them as a natural communication channel. The observation at KIC 8, 462852, covered this range and extended well beyond it, monitoring for any narrowband emission, any structured signal, any pattern that departed from the expected background of natural astrophysical radio noise. The result was published by Jerry Harp and colleagues in 2016. The Allen Telescope Array had recorded no anomalous signals from the direction of KIC 846282 across the monitored frequency range. No narrowband emission, no structured or repeating pattern. The radio background from that region of Cygnus was consistent with what would be expected from a stellar system producing no artificial radio output. This was a null result, not a confirmation that no technology exists there, since there are many reasons a civilization might not emit detectable radio signals, and since radio emission that is not directed toward Earth would largely not be detectable at 1,470 light-years. But it was the result of a careful documented search using a purpose-built instrument, and the result was negative. The data were recorded and archived. The result was published and entered the scientific record. KIC 8, 462852 had been listened to, and it had not spoken. Null results in science occupy an interesting position. They do not resolve questions, but they do constrain them. The absence of detected radio signals from KIC 846282 does not establish that no intelligence is associated with the star. The absence of a signal at these frequencies and sensitivities only establishes that, during the period of observation, no signal of the type being searched for was detected above the detection threshold of the instrument. That is a specific, bounded, honest statement. It eliminates one range of possibilities: high power, narrowband, or otherwise structured radio emission in the monitored frequency range at or above the detection limit, without eliminating others. The null result is not a resolution, it is a data point, and a real one. It sits in the scientific record alongside the wavelength-dependent dimming measurements and the dip morphology analyses and the infrared excess constraints, contributing to the full picture of what has been ruled out and what has not. There is something worth noting in the way the megastructure hypothesis entered the public conversation and the way it was received. The response was not simply enthusiasm. Mixed into the public interest was a specific kind of hope, a quality that is familiar from the history of SETI research more broadly, from Lowell's canals on Mars, to the WOW signal, to the fast radio bursts of the 2010s. Wherever an observational anomaly appears that cannot immediately be explained by known natural processes, a portion of public attention turns toward it and holds a particular kind of open expectation. The anomaly becomes a vessel for a question that is older than the specific observation. Are we alone in this? That question is legitimate and large, and it does not require KIC 846282 to answer it. The star's behavior is genuinely anomalous. The anomaly has not been fully explained. Those two things are true, independent of what is causing the dimming, but the presence of a genuine unexplained anomaly does not by itself constitute evidence for a specific proposed explanation that the data do not support. The question of what is causing the dimming and the question of whether we are alone in the universe are not the same question, even when they feel connected. The professional community has held that distinction carefully. Researchers who work on KC 8462852 have been consistent in separating the genuine scientific interest of the anomaly, which is substantial and ongoing, from the extraterrestrial interpretation that attached to it in public discourse. The star presents a set of observational characteristics that natural explanations have not yet fully accounted for. That is a real and open problem in stellar astrophysics, and it is interesting on those terms alone, without requiring a more exotic frame. The tendency in public discourse to collapse the unexplained into the extraterrestrial has been, at various points, an obstacle to clear understanding of what the actual scientific status of the mystery is. What is known is that the dimming is real, that it is wavelength dependent, that it involves fine dust, and that the complete picture of what is producing that dust and sustaining the behavior over decades has not been established. That is the accurate summary of the evidentiary situation. It is genuinely interesting on those terms. Wright's position on the megastructure hypothesis, elaborated over years of writing on astrowrite, reflects a more general principle about how exotic hypotheses should be handled in science. The instinct to exclude a hypothesis from consideration before testing it, to decide in advance that a certain class of explanation is too improbable to warrant examination, is not always a sound scientific impulse, even when the class of explanation in question involves intelligence of non-human origin. What counts is the evidence. If the evidence excludes a hypothesis, the hypothesis should be set aside. If the evidence is consistent with a hypothesis, the hypothesis should remain in the list of candidates until something more specific rules it out. In the case of KIC 8462852, the wavelength-dependent dimming provides a specific physical constraint that is inconsistent with large opaque solid structures. That constraint is sufficient to place the megastructure hypothesis at the very bottom of the probability ranking. Wright has not argued otherwise. His argument has been methodological, that the test should happen and that the test should be what decides. The test has happened, the result has been noted. The formal constraint imposed by the wavelength dependence is worth dwelling on because it is the clearest single piece of evidence that most directly addresses the megastructure hypothesis on its own physical terms. The prediction of the Dyson swarm model, or any model involving large engineered solid opaque orbital structures, is that occultation by such structures should block light in a wavelength neutral way. The observation at KIC 8462852 is that the dimming is not wavelength neutral. The two things are in tension. If the dimming were gray, if it blocked all wavelengths equally, the megastructure hypothesis would be much harder to rule out on wavelength grounds alone. It is not gray. The non-gray character of the dimming is the direct physical reason the hypothesis is positioned where it is in the probability hierarchy. That is not a matter of scientific convention or aesthetic preference. It is a consequence of what the multi-wavelength monitoring campaigns actually measured when a dimming event was occurring at the star. Huan Meng's 2017 campaign, which observed a dimming event simultaneously in ultraviolet with Swift and in infrared with Spitzer, produced data showing that the ultraviolet dimming was deeper than the infrared dimming. The differential is physical information about the size and character of whatever is blocking the star's light. Large solid objects do not produce that differential. Fine dust does. The conclusion follows from the measurement. None of this means the mystery of KIC 8462852 is resolved. The dust explanation accounts for the wavelength dependence, but introduces its own questions about the origin, quantity, and replenishment of the dust. The secular dimming trend, the slow sustained fading across years and possibly decades, remains incompletely explained by any single model. The specific morphologies of the deepest dipping events, with their internal structure, their asymmetric profiles, and their duration ranges, have not been fully reproduced by any model proposed to date. The question of what is causing the dimming remains genuinely open. It is open at the level of natural astrophysical process. It is not particularly open at the level of the megastructure hypothesis, which the wavelength data have constrained strongly. Those are two distinct statements about two distinct things. The mystery is real, and it is interesting, and it is not yet resolved. The megastructure hypothesis is also real. It exists in the scientific literature. It was formally raised and formally tested, and the test did not support it. The Allen Telescope Array pointed its dishes at the constellation Cygnus in the fall of 2015, and the dishes listened. They listened across frequencies from 1 GHz to 10 GHz, covering the water hole range and extending well beyond it into the microwave spectrum. The data were recorded over the full observation period. The analysis was completed. Harp and colleagues reviewed the full frequency range and found nothing. No narrowband emission, no structured signal, no anomaly distinguishable from the ambient radio background of the cosmos in that direction. The result was a null. The dishes were pointed at a star 1,470 light-years away, in Cygnus, a star whose brightness was dimming in ways that no complete explanation had yet accounted for, and the frequencies across which a technologically advanced source might be expected to emit something returned only the quiet background of the cosmos. The data were entered into the scientific record. The question remained on the table. The dishes continued to move, as radio telescope arrays do, tracking the slow rotation of the sky overhead, and the star in Cygnus continued to do what it had always done, dim and recover, and dim again at intervals that no one had fully predicted, for reasons that no one had fully explained. 1,470 light-years away, its light still traveling. The papers continued to appear through 2015 and into 2016, each one working through a different angle of the problem. The scientific community did not abandon the problem once the public attention began to dissipate. The question had not changed. The data had not changed. The light curve with its irregular, asymmetric dips was still in the Kepler archive. The slow secular fading was still in the pixel-level photometry that Monte and Simon had confirmed. The wavelength-dependent dimming observed during active dip events was still in the multi-wavelength records. The absence of elevated infrared excess, the heat that a substantial warm debris field should be re-emitting into space, was still confirmed by Spitzer and Weiss data. All of these constraints were real. All of them needed to be accounted for simultaneously by any explanation that hoped to be complete, and no explanation had cleared every item on the list. The problem remained what it had always been, genuine, interesting, and unresolved. Wright maintained his list of constraints through this period: the secular dimming, the dip morphology, the wavelength dependence, the absent infrared excess, and evaluated each proposed model against all four. His consistent conclusion, stated publicly and in professional communication, was that no single proposed explanation satisfied all four constraints simultaneously. Fine dust accounts for the wavelength dependence. It does not easily account for the absence of infrared excess in the quantities implied by the degree of optical blockage. Cometary swarms account qualitatively for some aspects of the dip shapes. They require implausibly large reservoirs of material to account for the largest events. Intrinsic stellar variability has been evaluated and found insufficient to explain the specific dip morphologies. Instrumental artifacts were ruled out by Monte and Simon's careful pixel-level analysis. Each explanation handles part of the problem. None handles all of it. The checklist sits on the desk without a clean resolution. The megastructure hypothesis, tested against the wavelength data and found inconsistent, is at the bottom of the list. The dust models tested against the wavelength data and found consistent are higher up, but higher up is not the same as closed. What the paper by Wright, Sigurdsson, and Boyajian accomplished by formally raising the megastructure hypothesis in the scientific record was not what the public conversation sometimes assumed. It did not open a door to a confirmed discovery. It opened a door to a disciplined test of a specific class of explanation against specific observational evidence, and the test produced a result. The result was a constraint. The constraint placed the hypothesis at the lowest probability position in the ranking. That outcome is, in its own way, as useful as any positive result would have been. Science advances partly by ruling things out, by ruling out large, opaque, solid structures as the primary occulting material at KIC 8462852. The wavelength-dependent dimming measurements narrowed the field of candidate explanations in a real and permanent way. The narrowing is the contribution. It is not a spectacular contribution in the way that a confirmed alien construction would have been, but it is honest and durable and part of the record. The Allen telescope array's dishes tracked KIC 8462852 across the sky during that fall 2015 observation run. The monitors recorded the data in real time. The signals were analyzed against the background. Nothing was found in the frequencies being monitored. The observation was completed, the null result published, and the dishes moved on to the next target in the survey queue. The star in Cygnus went on dimming and recovering according to its own irregular schedule, 1,470 light-years away, its light crossing that distance at the speed of light, taking 1,470 years to arrive, carrying information about whatever was transiting its face when the light was emitted 14.5 centuries ago. The light arrives, the photomonitors record it, the archive accumulates the measurements, the curves are analyzed, the constraints are applied, the question is evaluated and re-evaluated. The case file is open on a dozen researchers' desks, and the search has been made, and a careful null result has been returned, and the question continues, not as a crisis and not as a resolution, but as something that has been genuinely, carefully looked at from many angles with good instruments by people who know what they are doing, and that has not yet given up its complete answer. After the Kepler Space Telescope's primary mission ended in 2013, the star-designated KIC 8462852 was left without a dedicated instrument. For a stretch of months, there was no single telescope assigned to watch it. The question of what it might do next, whether it would dim again, how deeply, on what schedule, was a question without anyone positioned to answer it. Into that gap came a distributed network of robotic telescopes spread across both hemispheres of the Earth, each one capable of being tasked remotely, each one able to hand the watch to the next as the planet turned and the sky changed. The Las Cumbres Observatory Global Telescope Network operates on a principle both practical and quietly elegant. By placing identical robotic telescope systems At sites across Hawaii, Chile, South Africa, Australia, and the Canary Islands, the network can, in theory, observe a northern hemisphere object like KIC 8462852 through nearly every hour of the night. When the sky brightens at one site and the star disappears into morning, it is already night somewhere else. The thread of observation does not break. It passes, hand to hand, around the circumference of the world. That was the instrument recruited to hold KIC 8462852 in view once Kepler had turned away from it. Not a single vast mirror on a mountainside, but a chorus of smaller ones, distributed and patient, watching in relay. The arrangement took time to organize. Boyajian and her collaborators needed dedicated observing time on the network, and dedicated time on any telescope costs money. The solution they reached for was not a grant application or an institutional allocation. It was a Kickstarter campaign launched in 2016, asking individual members of the public to contribute toward a fund for telescope hours. More than 1,700 people responded. The total raised exceeded $100,000. It was a small sum by the standards of large astronomical facilities, but it was enough to buy time on Las Cumbres, enough to be ready when the star next chose to dim. The people who backed that campaign were not professional astronomers. Most of them were simply curious. They had read about the star in a news article, or heard about it from someone who had, and they wanted, in whatever modest way the mechanism allowed, to be part of finding out that money was well spent. In May of 2017, the star began to dim again. The dimming event received the name Elsie, a convention adopted by Boyajian's team of assigning informal names to dipping events rather than purely numerical designations, a small humanizing gesture toward a data set that had accumulated a great deal of cold notation. Elsie arrived as a gradual sustained decrease in the star's brightness, detected in ground-based optical monitoring, and flagged quickly enough that the observing network could be mobilized across multiple wavelengths in something close to real time. SWIFT, a space telescope operated by NASA, contributed ultraviolet measurements. Spitzer, still operational in its infrared orbit, contributed thermal data. Las Cumbres contributed optical photometry from multiple sites. For the first time since the star had first been noticed, a dimming event was being watched simultaneously by instruments sensitive to 3 separate regions of the electromagnetic spectrum, the data streams arriving together, each one tracing the same event at a different frequency. What those 3 streams showed, laid against one another, was not equal. The ultraviolet curve dipped more deeply than the optical. The optical dipped more deeply than the infrared. The 3 instruments watching the same event from the same moment produced 3 different readings of how dark the star had become, and the hierarchy of those readings, shorter wavelengths blocked more, longer wavelengths blocked less, held within it a specific physical signature. Fine particles, dust grains small enough to scatter light selectively, to intercept the high-frequency ultraviolet more efficiently than the low-frequency infrared. Large solid objects would not produce that pattern. A body the size of a moon, or a spacecraft, or any structure large enough to be called an object in the ordinary sense, would block all wavelengths with equal indifference. The Elsie event did not do that. Its 3-way measurement offered, in the differing depths of those 3 curves, the clearest physical clue the star had yet provided about the nature of whatever was passing in front of it. Boyajian and colleagues published the Elsie analysis in the astrophysical journal Letters in 2018. The paper confirmed wavelength-dependent, non-gray obscuration, the dust interpretation already supported by earlier multi-wavelength work was further reinforced. The question of where the dust originated, how it was sustained, what was generating and replenishing it at the quantities required, and why it produced dips of the asymmetric complexity seen across the full Kepler dataset, those questions remained open. The LC data was the most precise and comprehensive contemporaneous measurement ever assembled for a dipping event at this star. It pointed in the direction of dust with more specificity than anything that had come before. It did not close the case. It simply illuminated one more edge of the space in which the answer, when it comes, will need to fit. Other streams of evidence reach further back. In a building in Cambridge, Massachusetts, the Harvard College Observatory holds an archive that has no precise equivalent anywhere else on Earth. Over more than a century, from roughly 1885 onward, astronomers at Harvard exposed glass photographic plates to the night sky, recording the brightness of stars in the same fields again and again for decade after decade. The archive contains millions of these plates, each one a thin glass rectangle holding a chemical record of the sky at a specific date and time. The project known as DASH, Digital Access to a Sky Century at Harvard, undertook the work of scanning, calibrating, and cross-referencing these plates, turning the chemical stains of old star images into digital photometric measurements that could be placed on a uniform brightness scale. KIC 8462852 appears on those plates. It was there before any astronomer alive today was born. The question the DASH project allowed researchers to ask was whether the star's brightness in the 1890s, or the 1920s, or the 1950s differed measurably from its brightness in the years of active Kepler monitoring. Some analyses of this historical record suggested that it did, that KIC 8462852 appeared to have been fading, gradually, across timescales of a century or longer, with estimates suggesting something on the order of 16% dimming between the late 19th century and the late 20th. The measurement involves careful treatment of calibration and comparison stars, and the photographic plate record carries more uncertainty than a modern digital photomonitor. Researchers have engaged that uncertainty seriously. The long-term trend, if it holds across the remaining calibration questions, represents something additional, not the sharp, irregular dipping events documented in the Kepler years, but a slow, century-scale quieting of the star's light that would need its own explanation, or that might share one with the shorter-term dips. The relationship between them not yet worked out. There is something in the quality of that archive, the glass plates, the chemical emulsions, the overhead light in the scanning room, the calibration work that translates a brown stain into a number on a brightness scale, that feels continuous with the work happening on modern photometric networks. The astronomers who exposed those plates had no knowledge of what would interest a researcher 100 years later. They were simply recording the sky as carefully as they could with the instruments they had. The patient accumulation of numbers carried across a century by institutional habit and physical preservation becomes usable evidence for questions not yet asked at the time of the recording. The star was there in 1895, in 1930, in 1968, a small point on a glass plate, its light arriving at the emulsion without announcement, recorded without comment, filed in a cabinet, surviving. The American Association of Variable Star Observers has been doing something similar, distributed across thousands of individual observers since 1911. The organization coordinates brightness measurements of variable and unusual stars, contributed by both amateur astronomers and professional observers, maintaining a publicly accessible database that now holds well over 200 million individual observations When KC 8462852 moved from Kepler's field of view into the gap before formal ground-based monitoring was established, it was AAVSO members, observers with privately owned backyard telescopes, contributors with access to small university instruments, amateurs with careful habits and consistent calibration, who maintained a photometric record. Each data point submitted to the AAVSO database represents a specific night, a specific observer, a specific measurement taken by a person who had looked up and found the star and held it in their aperture for long enough to record its light. Hundreds of such measurements accumulated for KIC 8462852 in those intervening years, each one a citizen-contributed thread in the observational record, each one keeping the data continuous across time that might otherwise have been dark. There is a quality to citizen science that is worth naming carefully. It is not simply a labor-saving arrangement, though it does distribute work across many hands. It is also a particular kind of attention, steady, voluntary, motivated by genuine curiosity rather than institutional obligation, sustained over months and years by people who find the object interesting enough to keep returning to it. The Planet Hunters volunteers who first flagged KIC 8462852 as odd were not paid for the work. The AAVSO observers who maintained its photometric record between missions were not professionally required to do so. The 1,700 individuals who backed the Kickstarter campaign had no expectation of anything in return except the knowledge that the observation would happen. That structure of voluntary distributed watching is part of the actual history of this case. It is not background. It is how the data came to exist. The star sits, tonight, in the constellation Cygnus. The constellation itself is a familiar shape in northern summer and autumn skies, the long neck and spread wings of the swan, the bright star Deneb at its tail, Albireo at the beak, the whole figure crossing the dense band of the Milky Way. KIC 8462852 is not visible to the naked eye. It requires a telescope to resolve it as an individual point rather than a contribution to the general luminescence of the Milky Way's plane. But it is there, approximately 1,470 light-years from the ground, an F-type star, somewhat hotter and larger than the Sun, burning at a surface temperature of around 6,750 Kelvin, its light taking nearly 15 centuries to travel the distance between it and Earth. That number, 15 centuries, carries within it a particular quality of remove. The light arriving at a detector tonight left KIC 8462852 at a time when the constellation Cygnus had the same shape it has now, but the humans below had different names for it, different ways of reading its arrangement, different stories told about why those particular stars held those positions in relation to one another. The light traveling through the intervening space during all of that human time carried no mark of the world it was moving toward. It crossed the gap indifferently, at the only speed available to it, and arrived at detectors built by the civilizations that had accumulated in the interval. The dimming events recorded by Kepler, the sharp drops, the asymmetric recoveries, the clustered sub-dips of those particular days in the Kepler timeline, were produced by whatever passed across the stellar disk at a time 15 centuries before the measurement. What crossed in front of this star to produce the Dip 800 event happened around the 5th century of the Common Era. The question of what it was is a question about something that occurred well before any instrument existed to record it, and whose echo, only now arriving at our photometers, is available to be examined. That displacement in time is not distressing. It is simply a property of the subject. All stellar astronomy involves it. What makes KEC 8462852 particular is that the echo, when it arrives, carries a shape that resists simple reading, not the clean, regular transit signature of a planet, not the smooth, expected variability of a known stellar class, but something with irregular edges, multiple depths, asymmetric slopes, and a long-term trend that adds a separate layer of behavior beneath the sharp events. The echo is complex. Decoding it requires attention across multiple wavelengths, comparison against archival plates from a century ago, multi-wavelength simultaneous observations in real time, crowd-funded telescope hours, citizen-submitted data points from backyard instruments. The complexity of the question has called into being a complexity of the response. The dust interpretation, fine, submicron particles scattering shorter wavelengths more than longer ones, producing the wavelength-dependent dimming confirmed in the ELSI campaign, remains the framework that fits the most features of the available data. It accounts for the asymmetric dip profiles, which resemble what would be produced by material with a trailing component moving across the stellar disk. It accounts for the wavelength dependence, confirmed by the 3 instrument observations. It sits comfortably within the absence of significant infrared excess, since fine dust at the right temperature and density might not produce the detectable warm re-emission that a large dense debris field would generate. It does not account for every feature. The secular long-term fading, slow across years, possibly slower across decades and centuries, if the historical record holds, requires either the same explanation extended over a longer timescale, or a second mechanism, or a more complete version of the dust model that has not yet been fully developed. The checklist of observational constraints sits on the desk, not fully resolved, the columns not quite aligned with any single entry. Researchers continue to work through it. The case file for KEC 8462852 is not closed. It is not cold. It is actively maintained by a community of professional and amateur observers, supported by institutional archives and crowd-funded monitoring campaigns, rate against a historical record preserved in glass plates and digitized by a project that has been running for years. The Las Cumbres network continues to hold the star in view, its geographically distributed sites, minimizing the observational gaps that any single location would introduce. When the star next dims, and it will dim again, on whatever schedule its own internal dynamics, or the material orbiting it, or passing through its line of sight determines, there will be instruments ready to measure it simultaneously across multiple wavelengths, and a community ready to analyze what those instruments return. The name Tabby's star, the informal designation that replaced the catalog number in general conversation, adopted from Tabitha Boyajian's name as a tribute to the work of coordinating so much varied observation toward a single anomalous object, carries within it something worth noting. Scientific objects receive informal names for various reasons: ease of reference, affection, the influence of a particular observer's public prominence. This one was named for the person who coordinated the labor, gathered the citizen scientists and the professional co-authors, ran the crowdfunding campaign, and maintained the ongoing observational effort across more than a decade of open questions. The star did not reveal itself to a single observer with a large instrument and a prestigious position. It revealed itself across a distributed community of people, paying careful attention, and the name it carries reflects that. Tabby's star is a name for an object that was found collectively and is still being investigated collectively. Its strangeness distributed across many people's screens, many people's archived data, many people's submitted measurements on clear nights from backyard observatories in the quiet hours. Tonight the star is in Cygnus, or below the horizon depending on the season and the latitude of wherever it is being considered. Its light is always arriving somewhere. Photometric monitors log it. Automated pipelines check it for deviations from its established baseline. Archives preserve the measurements. The observation does not stop between papers. It continues on its own low level of attention, the data accumulating, the record extending, the next dipping event approaching at whatever rate the physics of the situation determines, the instruments ready to receive it and measure its depth across wavelengths. The uncertainty that surrounds this star is not a failure of science. It is science working at the edge of what current data and current models can resolve. The observation is careful, the instrumentation is precise, the multi-wavelength approach is methodologically sound, and the result of all that careful work is a set of constraints that no single proposed mechanism yet fully satisfies. That is what genuine uncertainty looks like from the inside. It does not have a neat boundary. It has a shape, the shape of what the data rules out, the narrowing region where an explanation might still live, the list of features that any successful model will eventually need to account for. The shape of the uncertainty is more precisely described now than it was in 2015. It will be more precisely described still when the next dipping event is measured and analyzed. The open question is smaller than it was. It is not yet closed. There is something restful in that, held at this distance and this hour, a star 1,470 light-years away. In Cygnus, its light arriving at detectors built by curious people on a small warm planet, its irregular behavior recorded in numbers and stored in files that can be opened and examined by anyone with access to the archive. The numbers do not demand anything. They simply sit in their columns, patient, available, carrying the physical record of something that passed across the disk of a distant star at some point in the 5th century of the Common Era, and whose echo is still being read by instruments that did not exist when the signal began its journey. The light does not know it is being measured. It does not know what it means. The meaning, or the honest acknowledgement that the meaning is not yet established, is something the people doing the watching bring to it, their instruments and their attention and their carefully maintained uncertainty, all directed toward the same small point in Cygnus. The grass at the base of the Las Cumbres site in Chile is dry at this hour. The dome is open. The telescope has been tasked by a remote command sent from somewhere else on the planet, by someone who is perhaps awake at a desk looking at a monitoring screen, or perhaps asleep while the automated schedule runs through its queue. The instrument does not distinguish. It points where it is told. The field of Cygnus is either above the horizon or it will be, and when it is, the photometer will measure the brightness of KIC 8462852, as it does on every clear night. It can, and the number will be appended to the record, one more point on the graph that has been accumulating since 2009, one more entry in the long, patient list of measurements that constitutes what is known about this star. The record extends in both directions from the present. Backward, it reaches through the Kepler years and back further into the dash plates in the AAVSO archives, touching the glass emulsions of the Harvard collection and the submitted measurements of observers who are no longer alive, their notes and calibration values preserved in a database. They contributed to without knowing. They were building a resource that would be consulted decades later for a question about a specific anomalous star. Forward, it extends into whatever the next monitoring campaign will find, the next dipping event will show, the next multi-wavelength analysis will constrain. The record is open at both ends. It grew from the past, and it is growing into the future, and somewhere in that extension, in some paper not yet written, in some data set not yet collected. The feature that finally allows a complete model to close every item on the checklist may be waiting. It may not be. The patience required to sit with that is the same patience the star has been receiving from the people watching it since 2011, when the first citizen scientist typed the word into a discussion thread and flagged the light curve for a second look. The dimming events continue on their own schedule. They are not waiting for an explanation before they occur. They happen at the rate determined by whatever physical process is responsible for them, whether that process is cometary or intrinsic to the star's own behavior, or some combination of mechanisms not yet fully separated from each other in the data. The events are occurring now, in the sense that the physics producing them is playing out at the star's location in the present moment, though that present, by the time its light arrives at Earth, will be 15 centuries in the past from the star's perspective. Already complete, already finished, the material that produced the dimming having long since moved on. What is arriving at Earth now left the star sometime around the late 15th century. What is happening at the star now will arrive at Earth's instruments sometime around the 35th century. The observation is always of the past. The past is, at this star's distance, very old by the time it arrives. That thought sits comfortably at this hour. The star is 1,470 light-years away. Its behavior is still being worked out by careful people with good instruments and a long accumulation of data. The answer is not yet fully in hand. The observation is ongoing. The case file is open on a dozen researchers' desks and in the monitoring queues of a distributed global telescope network, and in the archives of the Harvard plates, and in the AAVSO database with its hundreds of citizen-contributed measurements, and in the published papers that have been adding, year by year, one more constrained edge to the shape of what is still unknown. The star itself holds no record of being watched.